morning or afternoon or evening or whenever you're watching this. The beauty of asynchronous education. Anyway, good morning for me. And we're going to continue talking about things that protect the brain. So we will talk about the meninges and the blood-brain barrier. Now the meninges, these are 3 layers of connective tissue, and they surround the entire brain and spinal cord. Right. So they are there for protection. It helps support and protect the brain and spinal cord. And it contains the cerebrospinal fluid. The subarachnoid space is where the cerebrospinal fluid will be circulating and also protecting the brain and spinal cord. And it gives the meninges give another layer of protection. It's a layer of padding between the brain, the mushy brain, and the hard, bony skull. So it's there for support and protection. So let's talk about the 3 layers. From outermost to innermost, so the one that's closest to the skull. From outermost is going to be the dura mater. That's going to be more, it's like leather. It's kind of a leathery, unstretchable, thicker membrane. And that's on the outside. And I'm going to mention the tentorium cerebelli. Tentorium cerebelli, and I have another picture for you. So we have the meninges that surround the whole brain and spinal cord. This is me drawing with PowerPoint. And what it is you have to have a space for the brain stem to come through. And so think about it. Your brain is covered by the 3 layers, and one of them is a fairly thick layer, and surrounded by a fairly tough ridge of dura mater, which is kind of thick. So if you were to swiftly bash your head to the side, your brainstem might squish up against the tentorium cerebelli. So here's an actual picture. So we're looking up at the brain. So here we are looking at cerebellum. There's going to be the pons, and we're looking up. And think how thick that is, and your brainstem is coming through there. And so if you bash your brainstem across this thick tentorium cerebelli, that can knock you out. All right, so the outermost layer is the dura mater. All right, next layer in is the arachnoid mater. And it's named from a spider's web because it's kind of soft and spongy and webby and open. And in that subarachnoid space, the space between the pia mater and the arachnoid mater, is where the cerebrospinal fluid is going to circulate. And then the innermost layer is the pia mater, which translates to pious mother, and I'll explain why it's called that. And this is very loose connective tissue right up next to the brain, and it's very vascular. So just some images for you. So here's the skin, here's your bone of your skull, and then the dura, arachnoid, and pia mater, and then we get to the brain. And this is going to be that arachnoid villi that we talked about. Right here is the superior sagittal sinus. So in our subarachnoid space, that's where the cerebrospinal fluid is circulating. And then how does it leave the brain? As it goes through this one-way valve into this blood vessel that carries blood out of the brain. All right, we got some gushy real pictures. This is the dura mater. See how leathery it looks as it's folded down? That's the dura mater. This is the falx cerebri. It's kind of like the tentorium cerebelli. It's an invagination of the dura mater into the space between the 2 hemispheres. So it's a kind of thick layer in between there. Got more gushy pictures for you. All right, so here's the bone. Here's the dura mater, leathery dura mater. Ooh, right there's that blood vessel, the superior sagittal sinus. Arachnoid, it's tough to see the arachnoid and pia mater, but the arachnoid mater is going to be the webby layer. So again, dura mater, arachnoid, and pia mater. And then here's my favorite one. I love this image. Isn't that a cool picture? All right, so what we got? We got scalp. And then we have the periosteum layer of the bone, and then here's the bone of the skull. This right here is the dura mater. This is a dissection that shows the arachnoid mater, and underneath this is where the cerebrospinal fluid would be circulating. Pia mater, look, that thin layer that just covers up the brain. Cool image. Okay. Now, why do we call it pious mother? Where did that translation come from? And basically, it's all kind of mistranslations from the 10th century Persia. 10th century Persia is where the seat of medicine was. Back then, Persia, which is modern day Iran, that's where the real medicine was happening. In Europe, they had barbers who were putting leeches on you and were bleeding you. So medicine and the knowledge of medicine back then was in Persia. And al is the word that means a swaddling cloth. What a swaddling cloth is what you wrap a baby in. And they looked at the brain and they did dissections of the brain. They said, look at the brain. It's wrapped in this membrane like you'd wrap a baby in a cloth. And so alum was a swaddling cloth, and that was what they were calling it. But that got mistranslated from swaddling cloth to mother. So they were kind of like saying, oh, this is where we wrap up the baby. Oh, they say, oh, the mom wraps the baby. So swaddling cloth or membrane got mistranslated to mother. So that's why it's all mater. And dura, mater, that makes sense. It's durable. Arachnoid, that comes from a spider, and it looks like a spider's web. But pia, that pia mater, it translates to pious mother. But what it was a mistranslation, because tenacious, it was actually supposed to mean a tenacious membrane, because it's right there, right up against the brain. And tenacious has the same root as pious. Tenacious is you really cling to something, and so pious, as if you're religious, pious kind of means you're tenaciously clinging to your faith. So that was a mistranslation. So what they meant tenacious membrane to mean was mistranslated to pious mother. Anyway, and we'll close out meninges with meningitis. Anytime you have itis, it means inflammation. And so meningitis is an inflammation of the meninges. It can be quite dangerous. And it can be viral, bacterial, which is very dangerous, fungal, parasitic, different ways. And it can cause death. It can cause blindness, deafness, and can be very contagious as well. All right, let's move on to the blood-brain barrier. What the blood-brain barrier is we don't want every single thing that's in our blood supply to be able to have access to all the neurons in the brain. So the BBB is a protection, and it describes the way the capillary wall is. So we're not saying that there's no blood in the brain. That's not what we're saying. We're saying that we're going to be real selective about what is in the blood that gets to enter our brain. And so the blood-brain barrier is a property of the capillary wall. And basically the capillary wall, it's continuous, it's not leaky. Capillary walls that lead to the kidney or lead to the liver or other parts that need to filter it are very leaky. It's real easy for stuff in the blood to get into the liver and kidney, but it's not easy for stuff in the blood to get into the brain. And what the BBB looks like is the endothelium of the capillary wall is continuous, not leaky. And there's another layer of astrocytes. Astrocytes put their little arms and wrap them around the capillary wall. So it's still another layer that stuff in the brain would have to get through. Plus, then there's another layer. There's a thick basolaminar layer that surrounds the capillaries. So here we go. Here we have a capillary wall. And we can see the capillary wall is continuous. It's not leaky. So anything that wants to get from our blood into our brain has to be able to cross the wall, and not everything can. And then there's a basolaminar membrane, and then there's going to be, where's my astrocytes? So here are some astrocytes, and astrocytes kind of wrap their arms around it. And so the stuff is going to have to not only get through the capillary wall, but get through the astrocytes in order to get into the cerebrospinal fluid. All right, so it's all real tight junctions, and it makes it be a selective barrier. So what can cross and what cannot? So some things can cross. Now it's regulated, all right, but so small lipid-soluble things can easily cross. And pretty much all the drugs that human beings take for fun, alcohol, cocaine, cannabis is very fat-soluble, heroin, they all easily cross. Anesthetics, don't take those for fun, but drugs, a lot of those recreational drugs can easily cross. They're either small or lipid soluble. All right. Glucose can cross because you need it in your brain, but that is going to be transported in. So there's transporter proteins to get the glucose and the amino acids in. Also, some fatty acids and oxygens can certainly cross, and CO2 can certainly cross as well. But what really cannot cross, typically large water-soluble things. Now, glucose is fairly large and water-soluble, but we actively pump that in because our brain needs it. But generally, large water-soluble cannot easily cross. And that's nice. It means that wastes and toxins and most drugs, there's some disadvantages there, cannot easily cross in. 95% of the drugs that we take orally cannot cross the brain and cross the blood-brain barrier and get into the brain. So it's good in that every single thing we eat or take doesn't have easy access to our brain, but it can be a problem. So that's advantages and disadvantages. It can be a problem in that sometimes you need to treat brain disorders or treat a brain tumor, and it can be hard to get the drugs in there. So they're looking at other technologies. Sometimes they'll use ultrasound or nanoparticles. They attach some substances to viruses and let them in. So they're being real creative to get some stuff in. But the blood-brain barrier, its main function is to keep a lot of the things that are in your bloodstream from easy access getting into the brain. So function of the blood-brain barrier, protection from foreign substances, and protection from all the neurotransmitters and hormones and electrolytes. So you don't want too much potassium getting in. So you eat 11 bananas and the amount of potassium could really be devastating in your brain. So we were particular on that one. Remember, the CSF will pump in sodium, but it doesn't allow potassium in. Pumps out potassium, actually. And helps maintain a constant environment. Now, some things can break down the blood-brain barrier. Hypertension, high blood pressure. Basically, it can open up that blood-brain barrier. A developmental mishap. So sometimes the BBB is not fully formed at birth. Let's see, microwaves, not just your microwave oven, but the big old industrial microwaves. Exposure to bad big microwaves can damage the BBB, and radiation can as well. Infection. Exposure to some infectious agents can open up or break down the blood-brain barrier. And injury, so some trauma or ischemia or inflammation and pressure can break down the blood-brain barrier. And we're seeing a number of diseases may be due to that. So MS, one theory of MS is there was some infection maybe you had as a child and that did some damage to the blood-brain barrier. Or a trauma. So that can be quite problematic if things that you don't want to access your brain can now get access to it. All right, and let's see. Normally, the blood-brain barrier is pretty tight, but there are a few places where it is a little leaky, where the blood-brain barrier is weak. And I'm going to come back to this one, but the hypothalamus. Hypothalamus, remember, one of its many functions is it produces hormones. It itself produces oxytocin and vasopressin. And so you need to, and it has to be open to feedback. So as you release, let's say GnRH, it goes to the pituitary gland to make FSH, which goes down to your ovaries to make estrogen, and then estrogen has to feed back to shut off the GnRH from your hypothalamus. So the hypothalamus has to be open to hormones. So hypothalamus, around the hypothalamus, the BBB is weak, so hormones can access the hypothalamus. Same with the pineal gland. Pineal gland also secretes hormones. It secretes melatonin. So you need access to the bloodstream because it responds to hormones. And same thing with the posterior pituitary. All right, it's going to respond to hormones. And the last place that BBB is weak, I find this just so cool. The area postrema, also called the chemotaxic zone or the vomiting center of your brain. So it's in your brainstem. It's the vomiting center, and when a toxic substance enters your bloodstream, All right, it goes throughout your body, and most of the areas of your brain it can't get to because of the blood-brain barrier. But one area of the brain, because the BBB is weak, it can get to the vomiting center. So that can signal the brain to say, hey, barf now, vomit now. But isn't that beautiful? Isn't that fabulous how it works? You ingested a toxin, and one of the only places it gets to go to in your brain is the part of the brain that says barf. It says vomit, to get it out, hopefully try to get it out of your system. So before more harm is done. So I find that neat, that the area postrema has a weak blood-brain barrier. All right, we'll close it out and we'll start to talk about the blood supply of the brain in the next video.